Now, turbulent flowing tubes. So far we already know how to calculate the friction factor, Nusselt number, and the heat transfer coefficient for laminar flowing tubes. When we have the turbulent flow, so it means the Reynolds number is sufficiently high, fully developed and turbulent flow. So we can say it's greater than 10,000. The Reynolds number is greater than 10,000, isn't it? So if we have some smooth vibe, okay? So for smooth vibe, actually all these correlations you can see here, this is derived from some benchmark experiment because it is nearly impossible to analyze the turbulent flow or fully developed turbulent flow theoretically. So people did a lot of experiment and all these correlations for the friction factor, the Nusselt number, it is derived from benchmark experiment. This is called the Pettigrew equations, well-known equations for smooth tubes. When we have smooth tubes and the Reynolds number is high and it is a fully developed flow, then we will use it. So basically, you need to use it for when you will prepare your heat exchanger report. So this is the expression. F is the friction factor, R is the Reynolds number. Here is the Reynolds number range. It could be like 3,000 to this, 50,000. So once you know this friction factor value, for turbulent flow, you need the friction factor value. There are different ways. You can use the Modi charts. We'll discuss it later. But once you know this friction factor value, then you can put it here in these expressions. You can put it here, and then you can get the Nusselt. So this is the one way, okay, that how we can calculate the Nusselt number or the heat transfer coefficient for turbulent flowing tubes. Okay, so this is the first one. Now you can see very general easy friction factor expressions. So for fully developed flow in a smooth tubes, you can use the simple correlations with the friction factor. And basically, once you have this friction factor value, you can use these Corbin equations. You can only use these correlations if your conditions, initial conditions, satisfy this. So Reynolds number, it has to be greater than 10,000, and the Prandtl number, it should be within this value. If your problem meets this criteria, then you can use it. Okay, and then you can calculate the Nusselt number. So, but all these things, it is the very first one, and then it is the improved one. So both these two correlations, it has some sort of accuracy issue. So for better accuracy, you can use this Dittersburg correlations. So now the question is, if you ask me, look, I actually want to use this instead of this, it's fine. But if you really want better accuracy, you should use this one right now. So for the Dittersburg, you can use this correlation. This is more advanced. You go here, this Nusselt number correlate, all these correlations, it is for the Nusselt number calculations and all for the turbulent flows, but for different conditions. This is a more comprehensive. You can see one small n here. This, the value of this n, it could be 0.4 or it could be 0.3. So if it is a heating problem, so then you need to use this value for 0.4. If it is a cooling problem, you need to use it as 0.3. Now, when so this is, we will use it for many problems. When the variation of the properties is large due to the large temperature differences, then you can use these correlations. Okay, you can use this correlation. So you will see, but this is this correlations here. You look at the Reynolds number conditions and the Prandtl number conditions. Once you use this, still it should have some accuracy issues. Sometimes you can get some error up to 25%. So if you really want to see high accuracy, If it is the turbulent, then just use the second pair of equations. Here is the um, equations, and here is the conditions. Or you can use these correlations. So if you ask me how I will get this F, we already know the formula for F. So here, uh, here actually, we know the formula for F, how we can get the patience factor, and later on I'll show you how to get it from the charts. So this is all these correlations. This is just an improvement. So initially we had this, then they developed some, then it is the more developed one, and then this we can say it will give you more accuracy. If you have the flow inside the tube, I mean the analog tube, so like say the double pivot exchangers, so then this is how you will calculate the hydraulic diameter, and this is how you will calculate the Nusselt number for the inner and the outer surface. This is for the inner, this is for the outer surface, and you know, so we will here is the table. You can use it for the number 5. So you need it for when you will actually do some projects related to the heat exchangers. So that's some very short descriptions, like how you will calculate the turbulent flow in tubes. We'll solve problems, and in the videos we will discuss more comprehensively like how you can use this. But this is pretty straightforward. You just need to select the appropriate correlations for your prop based on the given conditions, and then you need to calculate the Nusselt number, okay? Or you need to calculate the Hayes. So you can calculate the Nusselt number at first, and then you can calculate Hayes. So that's it, and we'll discuss it during the lecture.